Hey everyone, my name's Arnav, and I'm here to give a rough solution outline to contact tracing from the 2022 NAC. So in contact tracing, you're given this idealized disease which leaves people asymptomatic but contagious the day after they catch it, and symptomatic 2 days after. Once a person is symptomatic, they will isolate and will not meet with any new people. There's also a single patient zero who contracted this disease, and everyone who gets the disease from there can trace their infection back to this patient zero. Unfortunately, we don't know this patient zero, and we don't know which contacts have resulted in transmission. So, given this uncertain state of the world, how can you determine who is actually infected? So one pretty natural approach is to just iterate over all people who could be patient zero and try and determine who's infected if you fix a patient zero. However, this approach still has a lot of uncertainties. We still need to determine who could be infected and which contacts actually result in transmission. So, one observation is that some contacts are guaranteed to not actually result in any kind of transmission. If a person A has contact with somebody on day D, we know they could not have become infected on day D minus 2 or before. And that's because 2 days after a person gets infected, they quarantine, they isolate, so they won't have any more meetings. Therefore, if each person, we only need to consider at most 2 days of contacts, and we can just remove all contacts that aren't within a day of the person's last contact. So this helps. Now, every contact that we consider after this pruning could potentially result in infection. So fix a person zero. Now we want to compute these two tables. One table says, is it possible for person A to become infected on day D? Another table is it possible for person A and person B to have contact on day D? So this problem would be pretty straightforward if we could prove the following claim. That it's possible for person A to get infected on day D if and only if there exists some person B such that A and B meet on day D and B can get infected on the previous day. This is clearly true if it's impossible for A to be infected on the previous day, because there's no other way they could get infected. However, is it possible for person A to get infected on day D if it's also possible for them to get infected on day D minus 1? And it actually turns out that it is. The only way that B could get infected before is if A infected B, either directly or indirectly. However, there's no way for this kind of cyclic A infects B, B infects A situation to happen because each person is only contagious and asymptomatic for a day. So if for B to catch it from A and then reinfect A, we would need at least 2 days, and that contradicts the setup of the problem. Therefore, even if A can get infected on day D minus 1, there has to be some alternate series of infections such that A can get infected on day D, given that they meet person B that gets infected the day before. I know I said that kind of quickly, so feel free to pause the video and look at these two slides for the proof. Once we've made this observation, the implementation is pretty straightforward. We can fix each person as the patient zero, and then we need to compute these two tables. Is it possible for a person to get infected on a day, and is it possible for two people to meet on a given day? Computing this can be done with DP, DFS, BFS, whatever kind of pathfinding algorithm in a DAG you prefer. And if you try for each possible patient, it'll take time proportional to the number of people times the number of contacts times the number of days. However, you can implement this a little more efficiently by considering all patient zeros at the same time, but this optimization isn't needed to pass the problem. Hope you enjoyed!